So let's get started to the plastic analysis and design of steel structure, and this is the introductory class, and we will see the basic concept behind that is used behind the plastic analysis and design. To begin with, we'll start a comparison between elastic analysis and plastic analysis. As a designer, you should be very confident and very clear about the behavior of the material under the action of load. And here the material is structural steel, and for testing the properties of structural steel there is one good test, that is the tensile strength, and we do it in UTM, and in that uniaxial load on the specimen, and continue to apply load till the failure takes place, and simultaneously we are drawing the stress strain curve. So eventually we get a stress strain curve similar to this. This is not the exact variation, but similar to this variation we will get. So we know that this is the point of zero stress and zero strain, and up to point A, which is also referred to as the proportional limit, the stress is directly proportional to strain. So this credit goes to Hooke's law. Beyond that, there is some jump. This jump depends upon the method of testing and the rate of loading. But this point C, and we denote it by Fy. This is also designated as lower yield strength, or Fy, yield strength of the steel. So after this, some linear portion is there in which there is increase in strain without any increase in the stress. Beyond this point D, there will be strain hardening, and we see that material will again start to take some load. The basic difference between elastic analysis and plastic analysis is the permissible design load. We generally consider the stress strain curve of structural steel, and in elastic analysis we overlook the portion beyond the elastic limit. So beyond this elastic limit we are not considering the strength of the member, and this is a crime that you are underestimating the strength of structural steel. You are considering the strength up to first yield point only. So what is permissible design stress? It is nothing but this value Fy, corresponding to this value. This value is called as Fy and divided by some suitable factor of safety. So this was the principle we used in working stress method, whereas the actual strength or the failure strength of the material is Fu. So based on this, I will show you a interesting video on cricket. So hope you will enjoy it. So let us see a small clip.
He's going to be close here. Yes, he's been given.
And the match is now wide open. Just take a look. The angle.
Yeah!
Celebration for England, disappointment for the huge number of Indian fans in the crowd. That might be the death knell for India in this NatWest Series final.
What we find in both the cases, India actually won the match. First match India won by 5 wickets, and the second match we all know it went up to the wire and eventually India won. So in both the cases the commentator underestimated this remaining strength. With the advancement in research and better understanding of the material behavior led to the exploration of restricted portion beyond the elastic limit. So when we felt confident about the material, we tried to explore this region, the region beyond the yield point in the stress strain curve. And in plastic design, what we do, we use the full potential of structural steel without compromising the safety and serviceability requirement. So in plastic design, whatever section we are giving, they are very efficient as well as economical also, because considering the higher strength of the material. Plastic design also deals with the collapse mode, which converts the structure into mechanism. So we will see what is mechanism. It uses the ductility of the steel, which ensures that large strain or large deformation takes place before actually collapse will take place. Now you can refer to page number 24. You will find some data given on the plastic analysis, and what it essentially means that it obeys the Hooke's law. Law means stress is directly proportional to strain. The other thing is we are assuming that the deformation is very small. So we are keeping the original dimension. We keep the original dimension of the structure for the analysis, and this is known as the first order elastic analysis. This is the first order elastic analysis we are doing in case of elastic analysis. So we have to move to plastic analysis. So as per IS 800-2007 code, page number 25 and 26, these are the some of the codal provisions that are given for plastic design. So first criteria is that the Fy value of the steel should be less than 450. Next is it should obey the stress strain characteristics. So this part is the yield plateau, and we have to use this idealized stress strain curve, wherein up to elastic limit there will be linear variation, and this part which is referred to as elastoplastic, we'll see in some time. And beyond this point, when the strain is greater than yield strain, the value of stress will not increase, it will remain constant up to strain hardening. So what we are doing, we are considering only ductility. What we are doing, we are considering ductility of the material, in which there will be substantial deformation but it will not fail. So what it says that the yield plateau should be, this yield plateau should be 6 to 8 times that of yield strain. So this length should be 6 to 10 times that of yield strength. Yield strain means epsilon y, and epsilon sh means strain hardening. So this ratio should be around 6 to 10. The ratio of Fu to Fy, this value somewhere here it will be the value for Fu. So ratio of Fu by Fy should not be less than 1.2. Then elongation should be greater than 15%, and steel should be capable of exhibiting the strain hardening capacity. Should also follow these criteria also. So these were the criteria of the stress strain. So member should be hot rolled, it should be either compact or plastic. Then the cross section should be symmetrical about the axis perpendicular to the axis of rotation. At first point, we should understand the behavior of a beam in plastic analysis. A simply supported beam, and suppose it is having it can have any section, it can be having a elliptical, square, rectangular, any section it could have. We know that when the load is increased, bending moment will also increase. Increase in bending moment, there will be more deformation take place. Deformation corresponds to strain, so value of strain will increase. So when value of bending moment increases, then it will lead to increase in the corresponding values of stress and strain. So this basic background we should always remember that. First thing, when a load is applied, there will be bending moment. When a bending moment will add, there will be some deformation. Because of deformation, there will be stress and strain. Now what we do, we consider a steel beam simply supported at the ends, and the cross section is symmetrical and is subjected to some point load W at the midpoint. So we are dealing with beam, so instead of talking about load, we'll talk about bending moment and bending stress. So bending moment in this case will be WL by 4, point load at the midpoint, simply supported beam, maximum bending moment will be at the center, it will be WL by 4, and bending stress is nothing but bending stress F is equal to M by Z. So M value we can get from here and simply divided by Z. So now we'll play with the loads, we'll increase the load, corresponding values of bending moment and bending stresses will increase. So let's see, this is the stage 1, when bending moment value is such that it is less than the yield moment. The stress strain distribution across the depth follow the elastic bending equation. It is indicated in the figure. All the fibers are stressed below the yield stress. So suppose this is the cross section. So what will happen? Maximum strain will be at the extreme fiber. So what it is saying, that the value of moment is such that the strain developed is less than the yield strain, and corresponding to this strain the value of stress is F, which is again less than Fy. So both the stress and strain are less than the corresponding value required for yielding. So what we can say, that here M1, that is stage 1, is less than My. So now what we do further, we will increase the load. So bending moment will increase, causing more deformation. So this stress strain will increase. So let's see what happens next. So now in the stage 2, now we are applying a moment that is equal to my. What this my means, that the extreme fibers of the cross section begins to yield and the stress will be equal to Fy. What is the value at the extreme fiber? In this strain variation, we see that value of strain is corresponding to yield strain, so it is equal to Ey, and corresponding to that value it is Fy. Stress is equal to Fy. So the stress strain distribution across the depth is still linear. All the fibers other than extreme fibers are stressed below yield stress. So this is very important. What is happening because of the bending, this extreme fiber is having stress is equal to Fy, whereas rest of the fibers are having stress value less than Fy. So this is the end of the elastic zone, right? Earlier in working stress method, this used to be the permissible stress, and how we got that? By dividing a suitable with some suitable factor of safety. So this is the end of the elastic zone, in which the applied moment was corresponding to the moment which causes yielding. So now again we will increase the load, because we know that there is some residual strength in the material, because it is ductile, it will undergo deformation but it will not collapse. So what happens next? Now the moment that is being applied is M3 in the stage 3. Value of M3 is greater than My. So what will happen? The yielding start to spread into inner fibers. What happened in the previous case? The yielding point, or the value of stress was only in the extreme fiber. Now what is happening? All the portion in the cross section where value of strain is greater than Ey. So this is the portion where the value of strain is greater than the value of Ey. This portion will have the stress is equal to Fy. Again, yielding is starting from the extreme fiber. So the portion of section with stress is equal to Fy. This portion where it is shaded with black, where the stress value is Fy, it is said to be plastic. So in this cross section, this black portion is plastic, whereas the section where the stress is less, this is the stress distribution. This triangle is having value of stress less than Fy, so we'll call it this portion to be a elastic portion. So when we consider the entire cross section, we see that some portion is plastic while some portion is elastic. So this combined section where some portion is elastic and rest are plastic, we call it as elastoplastic section. So how we calculate the moment of resistance? Simply we'll take the moment of this stress and we'll use this stress distribution to calculate the moment of resistance if required. Now suppose further we increase the load. Now still we are not satisfied, because we want to play with the material. So now what we do? Increase the load, bending moment is increasing, deformation is increasing, stress strain is also continuously increasing. So now what happens at the stage 4 when bending moment is M4? Now it will be equal to MP. It is called as plastic moment. What is plastic moment? The yielding of the fiber spreads to the entire cross section and the section is said to be fully plastic. When the entire cross section is having the stress value equal to Fy, this section is called as plastic section or fully plastic section, and moment corresponding to that plastic section is called the plastic moment. So at this case what will happen? Plastic hinge will be formed at this point. Plastic hinge will be formed at this point, and what will happen? A plastic hinge is formed at this stage. After this, the deflection increases rapidly. resulting in collapse or failure. The neutral axis, this is called as equal area axis. Idealized stress distribution is shown here. So this is the stages to analyze the bending behavior of a steel beam in plastic analysis. Now to sum up, this is only the stress distribution. We will talk about stress. So suppose this I section is there. So the extreme fiber will have the extreme strain and extreme stress. So when the value of moment applied was less than my, the stress in all the fibers was less than yield stress. Now at the second stage, what we did, M2 was equal to My. That means the extreme fiber will have stress is equal to Fy. Then subsequently, when we increase the moment value such that it is greater than My, this value, and it is less than the fully plastic moment, what will happen? The portion from the extreme fiber will start to get plastified. Whenever the strain value will increase beyond Ey, it will get stress equal to Fy. Strain will increase, but value of stress will remain constant as Fy. So this is called the elastoplastic section, and eventually when load applied is such that moment produced is equal to plastic moment MP, in that case entire section is plastified and the stress in each fiber is equal to Fy only. Now again to summarize it, what we do, will see both stress and strain together for that same figure. What is happening in stage 2? The load is corresponding to yield strain, so the stress will be equal to yield stress. Now what we do in third stage, will increase the load such that the strain caused is 3 times that of yield stress. Some portion will be having stress Fy, the remaining portion will be stressed less than Fy. At the stage 4, it is approximately 6 to 10 times of this value. What will happen? The entire section will have the stress is equal to Fy, and at this stage the plastic hinge will form and the moment of resistance of this section will be 0. So it is right time to see some of the definitions that are used in plastic and analysis and design. So the first definition is plastic moment. We have heard this term plastic moment, and it corresponds to the moment MP. So what is plastic moment? Plastic moment is defined as the moment of resistance of a fully plastified section or a yielded cross section. Yielded cross section means the entire cross section is having yield stress Fy. So such situation we call the moment equal to MP or plastic moment, or we can say that the moment required to plastify the entire cross section or stress the entire cross section by yield stress Fy. Mathematically MP is equal to Fy into ZpZ. So Fy is the yield stress Fy and ZpZ is the plastic section modulus. We will see what is plastic section modulus in the coming slides. Next definition is yield moment. So what is yield moment? It is denoted by My. It is the moment of resistance of the cross section whose extreme fibers have reached the yield stress, whose extreme fibers have reached the stress equal to yield stress, or else we can define it as moment required to cause stress equal to Fy in the extreme fibers. And mathematically My is equal to Fy into ZeZ. So what is Zp? It is the plastic section modulus. What is Ze? It is the elastic section modulus. And we are considering about ZZ axis, which is the major axis in case of a beam. So another term is shape factor. So shape factor is defined as the ratio of plastic moment MP divided by yield moment My. So when we write, we'll get FyZpZ by FyZez. So Fy cancel out. So we are remaining with S is equal to, that means shape factor is equal to Zpz by Ze. We will always find this value to be greater than 1. It is the ratio between the plastic section modulus to the elastic section modulus of a cross section, and it is a geometric property in the plastic analysis. Like we are using Ze in elastic design, we are using Zp value in the plastic design. Now next term is plastic hinge. We heard the term that when the section is fully plastified, the moment is empty, and there will be plastic hinge will be formed. So let us see what is plastic hinge. So plastic hinge in a structural engineering beam theory is a term used to describe the deformation of the part of beam where plastic bending occurs. Plastic bending occurs means elastic bending refers to the state when the load is removed, the beam will return back to its original position, whereas plastic bending indicates that the deformation is going to be permanent. The concept of plastic hinge is important for understanding the failure of steel structure. So plastic hinge is a yielding zone in a flexural structural element developed when throughout the section the stress is Fy. Suppose this is the cross section, and throughout the section the stress is Fy. It has plastified and the stress value throughout the section is Fy. Such state is called as the yielding zone in a flexural structural element. Plastic hinges are formed at the point of maximum bending moment. Suppose it is a simply supported beam subjected to a point load at the center, the position where maximum bending moment will take place. So in case of simply supported, it will be under the concentrated load, and in case of cantilever, maximum bending moment is at the support. So plastic hinges are likely to be formed at the supports, but these are suggestives and it may change from case to case. And also plastic hinges are formed when the geometry of a section is changing. Suppose this is a cantilever beam having geometry like this. A portion of a beam is having EI approximately equal to 2EI, and this part is having EI is equal to EI only. So plastic hinge is likely to form here also, where the geometry is changing. Another point is this point where plastic moment is likely to be formed because it is subjected to maximum bending moment, and also at the point where deflection is maximum. So this is true in the case of simply supported beam. So this is an important slide. So plastic hinge is rarely a true hinge. It is a theoretical hinge having no capacity to resist moment. Thus at collapse, a plastic hinge behaves like a standard hinge permitting free rotation. So the difference between plastic hinge and elastic hinge, this is important. So for plastic hinge, the internal moment of resistance of the section is MP, whereas for elastic hinge it is 0. So the internal moment of resistance of the section is MP, though it cannot resist any further moment or any load, whereas elastic hinge is having moment of resistance equal to 0. The plastic section will dissipate large portion of energy transfer through it, the load applied by the internal work, and this dissipated energy is equal to load into displacement or moment into angular rotation. So here we consider moment into angular rotation. So suppose these are the two members, member 1 and member 2, and it is connected with a elastic hinge, that is real hinge. So what this hinge will facilitate, it will facilitate the rotation of this member. It is like a scissor. When this member moves, the rotation is not transferred to this member. So how we look at the plastic hinge? So suppose this is a simply supported beam, it is subjected to some point load. Because of the load, there is deflection like this. So since as long as the deflection is curved, we will say that it is a elastic deformation. And suppose the load is kept on increasing like this, there will be a point when the rotation will be like this. So this will be a straight line, and here it will not be in a position to resist any further load or moment. So the capacity of this section is now 0. Now it cannot resist any moment. But how much moment it resisted plastic hinge? It has resisted a moment equal to MP before getting into this state. So this is the difference between plastic hinge and elastic hinge. So this is the continuation from the previous slide, difference between elastic analysis and plastic analysis. In elastic analysis, we consider three equations of equilibrium, and and here we consider the bending moment distribution is defined as by assumed plastic hinges must be in static equilibrium. The bending moment distribution defined by the assumed plastic hinges must be in static equilibrium when the load is applied. In elastic analysis we talk about compatibility. Strain in one section is assumed to be equal to that in the adjoining section, whereas in plastic analysis we talk about mechanism. There must be sufficient number of plastic and frictionless hinges for the beam structure to form a mechanism. The ultimate or collapse load is reached when mechanism is formed. Here we talk about moment curvature relationship, that is m upon I is equal to f by y is equal to E upon r, whereas here we talk about plasticity. The bending moment at any section of a structure must be less than or equal to the plastic moment of the section for the safety and serviceability. So difference between structure and mechanism. So mechanism is a term that is generally used by mechanical engineering students, and in their mechanism what happens, it is a combination of number of links that are connected such that relative movement, relative motion is possible between these links. But however in our structure the relative motion is not permitted. It is also a combination of members, but relative motion is not permitted. So we will try to explain this with an example of a simply supported beam. So this is our simply supported beam subjected to point load, and this is the deflected shape. So this is the first deflected shape. It is curved, so we will say that it is elastic, and on further increasing the deformation will change like this, and finally the deformation will be like this. So at this point we can say that mechanism is formed. Now this is a plastic deformation, it will not come back to original position, and now it cannot resist any further movement. It is deflected shape is like this. Next term is the length of plastic hinge. So it is the length of the beam over which the bending moment is greater than the yield moment my. Suppose this is a simply supported beam. It is subjected to a load W. So it will have some bending moment like this. Now suppose we increase the load. Now the load is say Wy. So this ordinate will be equal to My. This will correspond to yield moment. For on further increasing the load, suppose now this load is Wp. So corresponding to this load Wp, MP is formed. So in the subsequent sides, this will be the region where bending moment is greater than My. So this region is called the length of plastic hinge. So plastic hinge will form here, but some portion of the beam to the left and right of the plastic hinge will have moment equal to yield moment. So this is called as the length of plastic hinge, like this. So there is a small derivation in which we'll assume a simply supported beam with a central point load, and the maximum bending moment will occur at the center of the beam only, and as the load is increased, the moment also increases, and at a stage fully plastic moment of the section MP is reached and the plastic hinge is formed at the center. So for this case we are trying to find the length of plastic hinge. So this load correspond to a load which will cause plastic moment. So the total length is L and length of plastic hinge is X. Length of plastic hinge is X. So this length will be L minus X by 2, and on this side this will be L minus X by 2. So what is the height? This is height MP. So by similar triangle what we can do, we can write MP divided by L by 2 is equal to My divided by this distance is L by 2 minus X by 2, M by 2. So we can write like this. So My divided by L by 2 minus X by 2 is equal to MP divided by L by 2. Now from here we will cross multiply. So we will get My by MP is equal to this term, entire term goes there. So it will be L minus x by 2 divided by L by 2. So 2 will cancel out. We'll get my by mp is equal to 1 minus x by L. So again we'll cross multiply. So when we solve, we'll get this value. So this is a small derivation, but it is very important. From here we can understand that for a beam simply supported beam subjected to point load at the midspan, the hinge length of the plastic zone is equal to the 1/3 of the span, is equal to 1/3 of the span. So what is x? X is the length of plastic hinge. What is L? L is the total span. So we can say that from this derivation, x is equal to span by 3. So for a simply supported beam, this x is equal to L by 3. 1/3 of the span will be formed as the length of plastic hinge. So we got the value mp is equal to wl by 4. We know that f is equal to m by z. We know that fy is equal to m by z. We are dealing with plastic hinge, so this value will be plastic moment and this will be plastic section modulus. So plastic section modulus for rectangular section is bh square by 4. So we can write mp is equal to fy bh square by 4. Similarly, when we write my, so we will write fy is equal to my means yield moment divided by elastic modulus ZE. So what is ZE? It is BD square by 6 or BH square by 6. So when we divide these two, MP divided by MY, we get this expression. So MY by MP is equal to 2 by 3, or we can say that MP is equal to 1.5 times. So MP is equal to 1.5 times MY. So this is a major contribution of plastic. So here in place of my, we have to substitute this value as 2 by 3 mp. Then we will get this value x is equal to L by 3. We have already seen how to calculate plastic section modulus ZP. ZP is nothing but moment of the area. So suppose this is the cross section and this is the equal area axis, and above the equal area axis the area is A1, and below the equal area axis the area is A2. Equal area axis means A1 is equal to A2. Now how we define plastic section modulus? It is the moment of the area about equal area axis. So what will be the formula? It will be ZP is equal to A1 into Y1 plus A2 into Y2. So we know that A1 is equal to A2 and it will be total area by 2 as it is the equal area axis. So we can write ZP is equal to A by 2 Y1 plus Y2, and plastic moment is equal to Fy into Zp. So these are some of the shape factors that are usually asked in competitive exam. The important ones I suppose is this one, white flange. So this is 1.14 is the important value which you should remember for competitive exam, and other minimum and maximum value. So for diagonal it is 2. So highest I think this is the value 2.34 for triangular section. So thank you.